So we started with this before we get into other examples. Blah, 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 blah. Okay, so first of all, graphing the function. And we talked about why would I plug in 2? Well, because the 0 of this parentheses actually is where the vertex is located for specifically a parabola, knowing that it has a vertex. Then offline we plugged in 0 and 4 to get those symmetrical points. It is neither because of the picture even or odd. It doesn't have symmetry of the y-axis anymore. But what the student did try to say is when I plug in negative x for x, by the way, that doesn't change the 2. This is not the same nor the opposite. Last hour, I foiled them both real fast to prove that. This is x squared minus 2x plus 4. This is negative x times negative x, still x squared. But this is a negative 2 times a negative x, 2x and 2x, which is positive 4x. And then negative 2 times negative 2. This term is the same as that, but this term is the opposite of that. It's over. The overall functions are not the same, nor are they completely the opposite. If they were completely the opposite, this would be negative and this would be negative. Then that would be opposite of. By the way, when you get opposite, what would that mean then? Opposite means what is the function? Starts with an O. Everyone's looking at me like an alien. Odd. Okay, is there extrema? Yes, that is the vertex. It's 2, 0. It's a minimum. Just remember this is where it occurs. This is what the minimum is. And then the last thing was how does it compare to y equals x squared? This is section 1.6. You're going to be answering this a lot. It went 2 right, or the recognition of knowing that this is 2 right from the parent function y equals x squared just by looking at the equation. Okay, so going offline for a second to cover the worksheet. Okay, back in the day, what you're going to have to do today is we're going to go into 1.3. Hopefully you can answer the questions without using your book, but use your book when necessary to get your what does everything look like. You better darn well have solidified that when you see an x squared with parentheses or not, that you know you have a picture of a parabola. Y equals x, linear, identifying it immediately. You better darn well know that if you have an x cubed, that it looks like this little wavy picture. Okay, from here to here. Is my pen working? Oh, there we go. I was waiting for my pointer. There it is. And then you better darn well know that when you have x in the denominator, you have asymptotes. More than likely vertical and horizontal. All right, and that's how we're going to approach it basic right now, but then in chapter 2, we're going to hit it hard. Okay, square root function, you better darn well know that it has a starting point because you can't take the square root of negatives and then rises like that, although at the end you'll see how we make changes here. And then what did I say E is between? What is E between? 2 and 3. So if I made you sketch e to the x without a calculator, just sketch 3 to the x or 2 to the x. E is 2.718 though, and we're going to hit E real hard in chapter 3. But then understand that when I raise a power or a number to a negative power, it just makes it a fraction. For all exponential functions, there is a horizontal asymptote. There's a y value that numbers approach when they are raised to certain exponents. Okay, even though we are going to have this later, you may be held responsible for remembering from last year that there's a vertical asymptote for a logarithm. And that the key point, the one thing I told you is logarithms are inverses of exponents. Let's look at the exponent function. Anything raised to the 0 power is 1. 0, 1 is an important point for the what is it called? The basic exponential function. The inverse of that is 1, 0. It's not a coincidence. That's the relationship. All right, but knowing that there's a vertical asymptote there and it rises is something you should remember. Remember, sine is 2 bowls, bowl, and it's odd. Cosine is the cosine kid. Hee-yah! Karate Kid. Absolute value functions of v. And then these two weird ones. Maybe Something about step functions, knowing how to graph this maybe a little bit. This one, if I ask you about the logistic function, we're not memorizing this. That's why I have this crossed off. But you got to be able to analyze the graph correctly. I will say this. I said this last hour as if anyone cared. If you have a petri dish or petri dish, which one is it? Petri. And you put a bacteria in there with food. One becomes what? Two. Two become what? Four become what? Eight become what? I'm done. Okay? But then 60 becomes 32. 32 becomes 64. If that growth was left unchecked, what would that bacteria eventually take over? The world. I don't care how small it is. If it keeps doubling, you'll eventually start seeing it. Then what you see doubles, and then what you see doubles, and then all of a sudden it takes over the room. Then after the room, it takes over all of Lockport, and it blah 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 blah. It becomes like the Blob. I don't know if you've ever heard of that movie in the 1950s. Okay, why doesn't it? Why doesn't it? Because in the petri dish, there's a limited amount of what? Like space or food that it's eating. So logistic functions actually treat what growth is realistically. Like eventually the bacteria takes off exponentially, but then because of the confinements of the experiment, the growth levels off to some parameter that limits its growth. Just like Earth. If we keep growing as humans population-wise, eventually there's going to be a limit to how many people can live on this planet. So that's why we have to go out in space and populate Mars or Europa or Titan. So here's the silly little questions you're going to be asked in this chapter. Okay, silly little questions you're going to have from your book, from your function book, naming which functions have these parameters. So the next one we'll do offline, and then 1 over x is the reason because you cannot have 0 in a denominator. The student said it much better than I did. I just want to make it go fast here. Okay, next question, still on that same group. Go ahead. What's LO6? It's a G, everybody. Get over my G's. Okay, so function has no negative numbers in their domains. Obviously, this is the one you better remember. The reason is 1, 0 is a coordinate, and logarithm has a vertical asymptote limiting that graph. We'll cover that in Chapter 3 in depth, although you did do it a lot last year. Okay, next, made that point of discontinuity a point of discontinuity, where the int function is just a bunch of steps with open and closed circles. The domain is still what for the int function, though? All real numbers. Okay, and then you'll get sick of those questions. Maybe I'll do the last one. Who are the 3 that are even without looking at your book? Students group number 7. Oh, that's fun. All right, and then I'm taking too long in the notes. I'm boring the student right here. Really bad. So here are some things that we should be aware of. Okay, say I was asked to graph this. E to the x, what should we actually graph? 2 to the x, very simple. What happens when I plug in 0 for x? What do I get for an output value? What's e to the 0? I don't care if it's whatever. 1, what's 1 plus 2? 3, so I plugged in 0, I got 3. All right, then I went to the graphing calculator and I looked at this. Well, this appears to be approaching 2, and that's what I mean. What did this do to the picture? What did it do to e to the x? What did it do? 2 up. It moved it 2 up. Remember, this was A, B, C, D. How do I analyze what happened to this function? It's increasing forever. Is this even or odd or neither? Wah. Okay, I just showed even and odd symmetry there. Or what I like talking with my other students from the past. What happens when I plug in negative x for x? What does this turn into? I don't have the time for this. 1 over e to the positive x. This is neither the same nor the opposite of what I started with. So that's how you test it algebraically. So you should be able to get these pictures maybe through using the graphing calculator for now if you're behind on your Math 3, but then after that you should make sense out of it. Without a graphing calculator to answer all these questions, what is the first coordinate I should plug in for x? -3. And I put it up here because this is not a vertex. There's not symmetry on both right and left of -3. This is the starting point. What's -3 plus 3? 0. What's square root of 0? 0. What's -0? 0. What's 0 minus 4? So your graph starts here. 1, 2, 3. 1, 2, 3, 4. And then what do I plug in next? -2. And you get 1 negative minus 4, which is -5. Oh, wait a minute. This graph compared to the parent function also got what? Flipped over the x-axis is the way you would say that. The next one I want to plug in is 1 because I like perfect squares. What's 1 plus 3? Square root of 4 is 2, negative. -2 minus 4 is -6. 1, -6. And then now we see this picture, and how does it compare to the square root of x function? It got moved 3 what? 3 what? Left. 4 what? Down. And what did that negative do? Flipped. And that's all the things we're going to do in 1/6 as well. Take it a lot further than that. All right, and then what's the domain? The domain is -3 to infinity. Oh my goodness. What's the range? Sorry. My hand's actually okay, just writing weird. What's the range? So -infinity to -4 with a bracket. And then is it symmetric with the y or x axis? No. So you should be able to do your homework, and actually shouldn't take you too long, even though I went the full bell here.